At the center of the Abell 85 galaxy cluster lies a disturbingly quiet galaxy. Its name is Holmberg 15A. At its core, studies suggest a black hole weighing tens of billions of times the Sun. Not a quasar. No violent radiation. No signs of destruction. Just a number. Published in scientific papers. And the first question is not what it breaks. It's what kind of object we are actually dealing with. To understand why Holmberg 15A has become such a difficult object for astronomers to interpret, we first need to place it within its true cosmic context. This is not an isolated galaxy drifting alone through space. It occupies one of the most influential positions a galaxy can have. Holmberg 15A is the central galaxy of the galaxy cluster known as Abell 85. In clusters like this, gravity draws hundreds or even thousands of galaxies toward a shared center over cosmic time. The central galaxy grows larger and more massive than its neighbors. These central galaxies are often called brightest cluster galaxies, not simply because they shine more brightly, but because they represent the final destination of countless mergers and interactions. Holmberg 15A is one of the most extreme examples of this class. The cluster itself lies roughly 700 million light-years from Earth. This distance places Holmberg 15 comfortably outside our local cosmic neighborhood, yet close enough that modern telescopes can study its structure in detail. At this scale, we are not observing the galaxy as it exists today, but as it was hundreds of millions of years ago. Even so, the light we receive is rich enough to reveal how stars move, how mass is distributed, and how gravity dominates the system. What makes Holmberg 15A especially notable is not just its size as a galaxy, but what appears to reside at its center. Astronomers have estimated that the black hole in its core has a mass of at least 40 billion times the mass of our Sun. To put that number into perspective, the black hole at the center of our own Milky Way weighs about 4 million solar masses. Holmberg 15A would be 10,000 times more massive. Even among supermassive black holes, this places Holmberg 15A in an exceptionally rare category. Only a handful of known objects approach this scale, and most of them are found much farther away in the early universe. Some studies have even suggested that the true mass could be significantly higher than 40 billion solar masses. Depending on assumptions and modeling choices, estimates can climb well beyond that already astonishing figure. These unusually large mass estimates began to emerge in the late 2010s. When astronomers combined new observational data with improved modeling techniques, Holmberg 15 quickly stood out as an outlier. Importantly, these results were not based on a single observation or a single wavelength of light. Researchers used optical observations to map the distribution of stars, X-ray data to trace hot gas bound by gravity, and stellar dynamics to infer the mass hidden at the center. By measuring how fast stars orbit within the inner regions of the galaxy, astronomers can infer how much mass must be present to hold them in place. In Holmberg 15A, these stellar motions imply a gravitational pull far stronger than expected. What makes this even more intriguing is what Holmberg 15A does not show. Despite its enormous central mass, the galaxy is not classified as a quasar. It does not emit intense radiation from an actively feeding black hole. There are no signs of powerful jets blasting through intergalactic space. No overwhelming energy output that would dramatically reshape the galaxy. In many ways, Holmberg 15A appears surprisingly quiet. This calmness is precisely what makes the object so unsettling. According to many theoretical models, a black hole of this size should have left clear scars on its host galaxy, yet those scars are difficult to find. Holmberg 15A therefore sits at an uncomfortable intersection between observation and expectation. It looks ordinary in some respects and extraordinary in others, without offering an obvious explanation for the mismatch. Before we can decide whether this galaxy truly hosts one of the most massive black holes ever measured, we must ask a more fundamental question. How exactly was this mass determined? And how confident can we be in the methods behind it? Measuring the mass of a black hole is never a direct process. Black holes emit no light of their own, and even the largest among them remain invisible against the vast brightness of a galaxy. What astronomers measure instead is gravity. In the case of Holmberg 15A, the first clues come from the brightness of the galaxy's central region. The light emitted by stars near the core tells us how much stellar mass is present and how that mass is distributed. Under normal circumstances, this stellar light can explain most of the gravitational pull in a galaxy's core. But in Holmberg 15A, the brightness alone is not enough. The stars appear to be moving under the influence of something far heavier. To investigate this further, astronomers analyze the velocities of stars orbiting the center. By measuring how fast these stars move and how their speeds change with distance, researchers can reconstruct the gravitational field shaping their motion. This method relies on stellar dynamics, the same physical principles that allow us to weigh the black hole at the center of our own galaxy. Faster stellar motion implies a stronger gravitational pull, and therefore more hidden mass. In Holmberg 15A, the velocities of stars in the inner regions are unusually high, even when the contribution from visible matter is fully accounted for. This excess motion points toward an extremely massive central object. Another important piece of the analysis comes from the structure of the galaxy's bulge. The bulge is the dense, central concentration of stars, and its size and shape carry information about the galaxy's gravitational history. Over decades of observations, astronomers have discovered strong statistical relationships between the mass of a galaxy's central black hole and properties of its bulge, such as stellar velocity, dispersion, and total mass. These relationships are not exact laws of nature, but they work remarkably well across a wide range of galaxies. For most systems, knowing the bulge properties allows scientists to estimate the black hole mass with reasonable confidence. For Holmberg 15A, researchers applied these same correlations. They measured the bulge structure, the stellar motions, and the overall gravitational potential, then inferred the black hole mass that best fits the data. This is where the numbers begin to climb into uncomfortable territory. When these methods are pushed to their limits, they consistently suggest a black hole mass tens of billions of times that of the Sun. However, these methods were never designed with such extreme systems in mind. The correlations were built using galaxies far smaller and black holes far less massive than what Holmberg 15A appears to host. As astronomers extrapolate these relationships into unexplored territory, uncertainties grow rapidly. Small assumptions in the models can lead to enormous differences in the final mass estimate. Holmberg 15A lies well outside what scientists would call the safe zone of these correlations. It occupies a regime where the data are sparse and the theoretical foundations are less secure. This does not mean the measurements are wrong, but it does mean they must be treated with caution. At these extremes, astronomers are navigating with tools that were never fully calibrated for such scales. What we are left with is a mass estimate that is both astonishing and unsettling. The data suggest an enormous black hole. Yet the methods used to reach that conclusion begin to strain under the weight of the result itself. And it is this tension that opens a deeper uncertainty about the true nature of Holmberg 15A. If Holmberg 15 truly hosts such an extreme black hole, why does it deviate so dramatically from the well-established relationship between black holes and their galactic bulges? For decades, astronomers have relied on a remarkably consistent pattern linking black holes to the galaxies that host them. It is one of the quiet successes of modern galaxy physics. At the heart of this framework is a relationship between the mass of a galaxy's central black hole and the properties of its bulge. As the bulge grows more massive and more dynamically energetic, the black hole at its center tends to grow in step. This relationship appears again and again across different types of galaxies. From modest spirals to giant ellipticals, the pattern holds with surprising reliability. It suggests that black holes and galaxies do not grow independently. Instead, they seem to regulate each other through feedback processes that keep their masses in balance over cosmic time. Because this relationship works so well, astronomers often treat it as a cornerstone rather than a mere trend. When new observations align with it, confidence grows that our models capture something fundamental. Holmberg 15A, however, does not quietly fall into line. When its estimated black hole mass is placed onto this relationship, it lands far from where it should. This is not a subtle deviation that could be dismissed as measurement noise or statistical scatter. The offset is large, persistent, and difficult to ignore. According to the standard picture, a bulge like that of Holmberg 15A should host a black hole of impressive size, but not one that approaches the extreme values inferred from the data. In effect, the black hole appears to have grown far beyond what the galaxy around it seems to justify. The usual balance between galaxy structure and central mass no longer holds. When such a foundational relationship fails so dramatically, astronomers are forced into an uncomfortable position. Either this system is a rare exception, or the relationship itself has limits we do not yet understand. If Holmberg 15A is merely an outlier, then it represents an unusual evolutionary history, perhaps shaped by events rarely seen elsewhere. But if it is not alone, if other galaxies like it exist but remain undiscovered, then the implications are far more profound. Our models of co-evolution may be incomplete. Holmberg 15 thus occupies a pivotal role. It sits precisely at the boundary between a comforting rule and an unsettling possibility that the rule may not always apply. And if its central black hole truly is as massive as the data suggest, then an even deeper tension emerges. How can such an extreme object exist without leaving clear signs of disruption in the galaxy that surrounds it? If the mass estimates for Holmberg 15A are even approximately correct, then the galaxy should look very different from what we observe. By most expectations, it should be loud, violent, and energetically active. In many galaxies, black holes of far smaller mass reveal themselves through intense radiation. As they feed on surrounding material, they ignite as quasars, outshining their entire host galaxies. Holmberg 15A does not behave this way. There is no evidence of a powerful quasar phase underway. No overwhelming radiation dominates the galaxy's output. Even more striking is what this absence implies. A black hole of such enormous mass appears to be sitting quietly at the galaxy's center, neither aggressively feeding nor dramatically reshaping its surroundings. This calm extends beyond radiation alone. Holmberg 15A has not shut down star formation entirely. While it is not a prolific star-forming galaxy, it does not show the clear signs of complete suppression expected from strong black hole feedback. In many theoretical frameworks, powerful black hole feedback heats or expels gas, depriving galaxies of the raw material needed to form new stars. Over time, this process is expected to leave galaxies dormant and structurally disturbed. Yet Holmberg 15A shows no dramatic scars of such disruption. Its overall structure remains intact. The galaxy does not appear torn apart or violently reshaped. This presents a deep contradiction. If the black hole is truly as massive as estimated, then its apparent passivity becomes difficult to reconcile with our understanding of how energy feedback should operate. One possibility is that the black hole exhausted its most violent phase long ago. The energetic outbursts may have occurred in the distant past, leaving behind a system that has since settled into relative calm. Another possibility is more unsettling. It may be that even extremely massive black holes do not always behave as efficient engines of destruction. Their influence might depend more on environment and history than on mass alone. If this is true, then Holmberg 15A is not just an oddity. It is a reminder that size alone does not dictate behavior, even for the most extreme objects in the universe. But this calm exterior raises another quiet tension. If the black hole is not revealing its true mass through radiation or disruption, could its gravitational influence be telling a different story altogether? And that story may be written not in light, but in the motion of something we cannot see directly. Could the strange rotation of the dark matter halo be quietly pointing to a mass even greater than we have estimated? Beyond the visible stars and glowing gas of Holmberg 15A lies a much larger structure. One that cannot be seen directly, but dominates the galaxy's gravity. A vast halo of dark matter envelops the entire system. Dark matter does not emit light, absorb it, or reflect it. Its presence is inferred solely through motion, through the way stars and gas move under its gravitational influence. In most galaxies, the rotation of this dark matter halo follows patterns that astronomers have come to expect. Speeds rise, then level off, reflecting a balance between visible matter and unseen mass. Holmberg 15A, however, shows hints of something more extreme. Measurements suggest that the velocities associated with its surrounding halo are unusually high for a system that otherwise appears so calm. These elevated speeds imply a gravitational pull stronger than what the visible galaxy alone can account for. Something unseen appears to be adding extra weight to the system. For some researchers, this raises a provocative possibility. If the dark matter halo is rotating faster than expected, the mass at the center of the galaxy may have been underestimated. In this interpretation, the black hole inferred from stellar dynamics may represent only part of a deeper gravitational structure. The true central mass could be even larger than current estimates suggest. If that is the case, Holmberg 15A would move from being an extreme outlier to something even more unsettling. A system whose mass pushes beyond the upper limits of what we have confidently measured nearby. Yet this interpretation is far from certain. Dark matter halos are complex, and their motions can be influenced by the broader environment of the galaxy cluster in which they reside. It remains unclear whether the unusual velocities reflect an exceptionally massive black hole or a more distributed and intricate gravitational arrangement shaped by past mergers and interactions. In this sense, The dark matter halo acts like a silent witness. It does not announce its conclusions loudly, but its motion hints that the story at the center of Holmberg 15A may not be complete. What it quietly suggests is not certainty, but discomfort. A sense that the true nature of this system may sit just beyond the limits of our current measurements. And to understand what kind of object Holmberg 15A truly is, it helps to step back and compare it with other black holes that occupy the extreme edges of our cosmic catalogue. Only then can we begin to see whether it represents a familiar type taken to an extreme, or something fundamentally different. To better understand what makes Holmberg 15A so unusual, it helps to compare it with other black holes that occupy the extreme end of the cosmic spectrum, not to decide which is larger, but to see how differently such objects can exist. One of the most famous examples is TON 618. This object lies billions of light years away. Seen as it was when the universe was far younger, TON 618 is a quasar, meaning its central black hole is actively feeding at an enormous rate. The surrounding accretion disk glows intensely, releasing vast amounts of energy into space. Its growth is violent and unmistakable. Everything about TON 618 signals rapid accretion, extreme luminosity, and an early universe environment rich in fuel. Another well-studied extreme system is Phoenix A, located at the heart of a massive and turbulent galaxy cluster. In Phoenix A, the black hole is embedded in an environment overflowing with hot gas. Powerful radiation and energetic feedback interact directly with the surrounding cluster, shaping both the galaxy and its wider environment. Here, the connection between black hole activity and environmental disturbance is clear. The system behaves much like our models predict for extreme black hole growth. Holmberg 15A stands apart from both of these cases. It is far closer to us, and yet it shows none of the dramatic signatures seen in TON 618 or Phoenix A. There is no blazing quasar, no overwhelming radiation, and no obvious signs of a violently disturbed environment. Instead, Holmberg 15A appears quiet, settled, and almost reserved. This contrast is striking. Three black holes that may occupy similar extremes of mass, yet each embedded in a radically different context and behaving in radically different ways. This raises the possibility that Holmberg 15A does not represent the same evolutionary phase as the others. Rather than a rapidly growing quasar or an energetically dominant cluster core, it may belong to a quieter, later stage, a stage where the most violent growth has already passed, leaving behind an enormous black hole and a galaxy that has gradually relaxed around it. But this interpretation brings with it another layer of uncertainty. To reach such a mass without leaving clearer scars, the black hole's history may have been more complex than simple, steady growth, which leads to a final possibility that cannot be ignored. Could Holmberg 15A be the product of multiple black hole mergers, stitched together through a long and imperfect history of cosmic collisions? If Holmberg 15A truly hosts a black hole of such extreme mass, then its present-day calm may be misleading. The most important clues might not be found in what the galaxy is doing now, but in what it has already survived. In the environment of a massive galaxy cluster, the central galaxy is not simply sitting still. It is a gravitational destination. Over billions of years, smaller galaxies sink toward the center, merge, and add their mass to the growing core. Each merger brings more than just stars and gas. It can also deliver a central black hole of its own. And when two galaxies merge, their black holes begin a slow gravitational dance, spiraling closer over time. In principle, this process can repeat again and again. A central galaxy like Holmberg 15A could accumulate not one, but many supermassive black holes across cosmic history, eventually combining them into a single enormous object. This is one of the most plausible pathways to reach masses as extreme as those inferred for Holmberg 15A, not through steady feeding alone, but through a long sequence of mergers. But real mergers are rarely clean. When black holes approach each other, they do not simply fall together like drops of water. Their interaction with surrounding stars can reshape the galaxy's core in subtle but detectable ways. As two black holes orbit, they can fling nearby stars outward through gravitational slingshots. Over time, this can evacuate the central region, carving out what astronomers call a depleted core, a kind of hollowed-out center. Such a core is not an explosion or a dramatic rupture. It is a quiet scar, written into the distribution of starlight. The galaxy can look calm, while its inner structure remembers the violence. Astronomers have reported that Holmberg 15A shows characteristics consistent with this kind of depleted core. Its central light profile appears unusually shallow, as if the inner region contains fewer stars than expected. Alongside this, the stellar dynamics can also become peculiar. Past mergers can leave behind irregular motions, anisotropies, or velocity patterns that do not match a simple, undisturbed galaxy. None of this proves that multiple black holes merged here, but it does provide a coherent story that connects the extreme mass estimates to a plausible evolutionary history. In that story, Holmberg 15A is not a sudden anomaly. It is the end point of a long process, a galaxy that has spent billions of years collecting remnants from its surroundings and settling afterward. If this is correct, then Holmberg 15A may be something rare and valuable, a living relic, still present nearby, preserving the record of ancient collisions that shaped the largest structures in the universe. And that returns us to the quietest part of the mystery, a black hole that may have grown through repeated cosmic impacts, yet now sits in a galaxy that looks almost serene. If Holmberg 15A is the product of mergers, then the next step is to ask what those mergers imply about the type of system it represents, and why its present behavior differs so sharply from other cosmic giants. Holmberg 15A is not important simply because it may host one of the most massive black holes ever measured nearby. Its true significance lies elsewhere. It forces us to pause and reconsider ideas that once felt secure: the relationships between black holes and galaxies, the role of feedback, and the assumptions that quietly underpin modern astrophysics. Holmberg 15 reminds us that even the most reliable patterns may have boundaries, and that, beyond those boundaries, the universe does not behave to reassure us. An exception this large cannot be dismissed easily. It challenges whether what we call rules are truly universal, or simply descriptions of the cases we have understood so far. In that sense, Holmberg 15A is not an outlier to be explained away. It is a signal, one that suggests our picture of cosmic evolution may still be incomplete. If you want to continue exploring structures like this, places in the universe where data begins to strain our certainty rather than confirm it, you are always welcome to continue this journey with us, because sometimes The most dangerous thing in the universe is not a black hole. It is the moment we believe we have already understood it.